Okay, good afternoon, everyone. It's 2 o'clock. Well, in the UK anyway. 3 o'clock in the rest of Europe, and I think this is our last seminar for this academic year, so before the break. So I'm very happy to welcome Adrian and Uwe. We're both old friends, so I probably don't need to introduce them in so much detail, but it's very interesting. I always find seeing you two work together because I knew Uwe from a long time back when he was always very interested in what we were doing, but always complained that this is not the right way to do it. Because he was always very methodological about how things should be done in based on his background in category theory and algebraic specifications and model theory. Whereas what we did in graph rewriting was often a bit more pragmatic, maybe is the positive way of expressing that. And Adrian, of course, has a sort of more applied background in modeling and meta modeling and model transformation. So it's very nice to see these things coming together and see sort of what interesting and complicated things you can do with them if you put your mind to it. So yeah, so one of those complicated things, of course, is if you have models across different levels, and that's what they're talking about today. So I don't know who is starting, but please go ahead and start your presentation. Yeah.
Yes, thank you, Raiko, for the nice introduction and presentation of us. So I'm Adrian Rutle. I'm from Western Norway University of Applied Sciences. Together with me, I have Professor Uwe Wolter from University of Bergen. Both of us are reside in Bergen in Norway. And today we present a joint work with Fernando Macias from IMDEA in Madrid. The title is Multi-Level Typed Graph Transformations. So first, to give you some background and motivation. So in traditional model-driven software engineering approaches, we usually have a fixed number of levels, mostly 4 levels. This keeps about 2 levels for 2 abstraction levels for modelers. And as you know, while we are doing conceptual modeling, we don't want to be restricted to only 2 levels. We want to think freely about how things are related, at which kind of abstraction levels we use. It's up to our human mind to do these activities. So restricting ourselves to only a fixed number of levels will give some potential challenge, like additional complexity, mismatch with natural way of modeling, maintainability, separation of concerns, and all of these things. So we've been working around this challenge since early 2000s, and in our group also. Multi-level modeling was conceived already in the early 90s, actually, but it got momentum with the works of Colin Atkinson and Thomas Kuhne, Juan de Lara, Estaguera, and in our group, we were working with these things already almost 20 years ago. So one of the things which would be crucial to understand the rest of the talk is with this multi-level modeling hierarchies. So model hierarchies, they have multiple levels of abstractions, as you see in this picture. Here we start with 0 on the top. For some people, it's more easy to think of the 0 at the bottom, but we've switched this upside down, and you see it's because you want to also increase the number and put additional levels in between here without reindexing the levels here, but you have to reindex the levels below. Here we only consider the underlying graphs and not constraints like multiplicities or other kinds of OCL constraints, just to make it simple. Each element in these models will have a direct type in one of the models above itself. So it doesn't need to be directly and exactly the level above it, but it could be jumping. Let's say this arrow in the lowest level has actually a type in here, but this arrow in here has not a type there, but it has a type 2 levels above in e-reference. So the direct types can jump over levels, and each element has also a transitive type on the top. Yeah, so for example, this element G head had a type here, gen head, and a type here, machine, and all the way to top to the E class. And it has also a direct typing, which is total to the top level. You could call this top one for a linguistic metamodel or linguistic extension if you want. This is like concepts coming from the deep metamodeling and multi-level modeling. You don't need to worry so much about this right now. For our tooling, we have a tool called Multicore. In this, we've chosen eCore because of implementation reasons. We use eCore. In eCore, you have this meta model called where you have reflexive meta modeling in which it describes itself. You have e-class, e-references, attributes, data types, and like these simple things that you need in object-oriented modeling. So once we have multi-level modeling and multi-level modeling hierarchies, we also would like to manipulate these models to do all the sorts of nice things which you can do with transformation rules. So that's where the multi-level transformation rules or typed rules are coming in. So in this presentation, we only talk about transformation rules which change or manipulate the bottom level graphs, or the lowest level. But we've been also looking into changing 2 levels at the same time, or 3 levels, or even levels in between. But for now, let's have a look at a transformation rule. It looks like this. The structure is quite simple and recognizable for people who know graph transformation and model transformations. You have a from part, which is the left-hand side, a to part, which is the right-hand side, and it's typed over a local hierarchy. So it's a hierarchy of this rule. We have M1, which is typed over this big capital M1. And the type of the type is also presented, which is E class. And the same goes for the right-hand side. We will detail these flexibility ideas soon, but for now, it's enough to say that we would like to do this with horizontal and vertical flexibilities in mind. Horizontal means that we can, if we have a rule defined for this guy, we can apply to other branches in the hierarchy. And vertical means that if I add a new level in here, it should still be applicable. Or if I do more specializations, I can write more special rules. Then the line graph transformation rule is a cospan, as you see in this picture, where you have the interface is just a union of the left and right-hand side of the rule. Yes, so about the horizontal flexibility, as you see here, we have the rule which we showed earlier. So you have the same rule could be applicable by binding it to different branches in the hierarchy. You're not supposed to read all the details in here, but you just see that there are multiple colors and each color indicates one binding. So the red one binds to these 2 guys, and then it's applicable to this one here, the green one to these 2, and so on and so on. So this gives you a horizontal flexibility in the sense that if I have multiple branches, or if I have multiple occurrences of this of these patterns, I can still match it. If I was not using these ideas, I would need at least in this case 2 rules just to give the same functionality in the left branch, and in the right branch 2 more rules. And if I have multiple more branches, I would need even more rules. For the vertical one, this figure indicates this again, you are not supposed to read all the details here, but you see that you have the meta part, which fits into level 1, and the left-hand side fits level 3, right? And if we now come up with a new level here, level 2 in here, so the same rule should still fit here. It fits in here, and it jumps over this additional level which we just added and fits down here. So you see this rule, what it does, it deletes this task from this actor, and what happens when you run it, then the task will disappear from here. Even you can specify the rule more and put an additional layer here and saying that, okay, I don't want any role with any task. I want roles which are specialized to R1 and T1, and only these should be applicable here. So these two are variables which are matched in here and then applicable to the lowest level here. So of course there are different other options to achieve these things, but all these options might have some pros and cons. Here I will try to give some motivations for why we chose the way we are doing it. So one of the options is to use just normal two-level rules. I mean, normal, the way it's usually done. If I have this case, which we showed in the previous example, where you have a hammer consisting of a handle and a head, and you have a generator of a handle and generator of the head. And with a configuration like this, if I want the generators to generate parts, I would need one for the head and one rule for the handle, which means I would duplicate the same, almost exactly the same rule in two different rules. This would make the rule too specific, and it will be difficult to reuse in different branches, in different configurations. And here we see that each machine, in this simple example, will need a new rule, and each language or each branch will need a new a set of similar rules. And this would lead to proliferation of rules, which means that you will have multiple more rules than what you would require. There's another kind of rule, which is multi-level without the typing. This is quite nice, but it will be generating multiple parts with the same machine without any specific links between these two concepts. So what's the problem with this is that it's too generic. And it's not precise, which means that all machines will create parts, and they create all kinds of parts. So you cannot say a head generator will generate head, because the rule is saying machine generates parts. It could be that a head generator generates handle, and handle generator generates head, and so on. So it might create a few problems in this case. The idea which we are using is this multi-level coupled rule or multi-level typed rules, in the sense that we say create an instance of each specific part for each instance of machine that generates that part. So we basically set this pattern saying that if in one of the intermediate levels this machine is supposed to create this part, then it can create it. So in this way, we get both genericness and specific, like precision. So we can reuse it in different configurations, in different languages, and also it's precise enough to say only the right machine can create the right part. Yeah. So if we look at the traditional way of graph transformation rules, just to draw some parallels. So this is a slide from the tutorial on graph transformations. You may recognize this. So you have type graphs, and type graph morphisms. And as you see, the type graph here in this case, it's just a homogeneous one, or if it's heterogeneous, they put together. But in our case, we have so the rules are typed over a type graph, and the matches are type graphs. The rest of the story is well known for this audience, so you don't need to repeat it. But for our multi-level hierarchies, we require multi-level typed rules. And here we get quite a few new concepts, like chain of graphs, because it's not only one graph which is typing these elements in the left and right hand side, as you have in your graph transformations, but you have a chain of graphs in here. We have typing, which is given by multi-level typing. We will come back to this, where this is not a normal graph of homomorphism coming from here to one level in here, but it could go by multi-level typing. And also we have the concept of match, which is a multi-level typed morphisms. So morphisms are also type compatible with this in the sense of that the typing is going up at the end. So let's have a look at typing chains. So if you look at this hierarchy, as you mentioned earlier, so you have like these elements having types in the levels above with jumps being possible. So we have paths of graphs, right? So these paths will give us the direct types of all elements in the chain. So the transitive closure of the direct types could be equivalently described by a typing chain. So these are a family of partial graph homomorphisms with some conditions. And it looks like this. So the models at the bottom level, so this guy, H, is multi-level typed. You see this special kind of arrow. It's multi-level typing. And typing it over this sequence of graphs, this path of graphs, where you have a partial graph homomorphisms between them, except for the ones which are going to the top one, which is a total one, because we need to make sure that there's always a type defined at the top, right? So this is a multi-level typing, and this is a multi-level typed graph, and this is a typing chain. And if we cut here, then we can take out this guy, and this will be multi-level typed over upwards and so on. So this is the definition of typing chain. Uwe will explain this soon. Yeah, but just to give you an idea, the typing chain is a sequence of graphs with a natural number telling you the depth of the sequence, or the length of the length, yeah, of the sequence. And we have this family of partial graph homomorphisms where you make sure that every graph has a type upwards, and the top one is the morphism to the top one is total. We have transitivity and the connexivity of the, yeah. So the typing chain with multi-level typing, if you put it side by side, it would look like this. So this is Gn and going up to G0, and if you spell out all the links between these, it will look like this. And the links between H with the multi-level typing will be S1, and you have in the left-hand side. So let's go back a little bit to the multi-level typed rules and have a look at them. So the graph transformation rules, as you see here, with the LINR, the cospan, as well known for you. So this is multi-level typed over a typing chain. The MM with this font is representing typing chain. These are the multi-level typing links between the graphs and the typing chain. If we pack out these multi-level typings, you get all these sigmas, as you saw in the previous pictures, with, of course, the type compatibility between these three components of the rule. And if we again spell out the typing chain, the MM, so you see the backside. You see not the ones with the TG and the SDT, but the LIR and the MMN upwards to MM0 and all its typing. So this is a rule, right? This is a rule. There's a left, right-hand side, and the intermediate, and the typings, and the typing chain, which is on top in here, the local hierarchy, which we were mentioning in the beginning. Yeah, and the input here is this graph S, which is also multi-level typed over an own hierarchy. It doesn't need to be the same hierarchy as a rule, of course. It could be another hierarchy. And the match here would be a graph homomorphism, this mu, yeah, together with this typing chain morphism. The typing chain morphism is this beta F, sorry for the parenthesis. It is beta F, which translates the types in here, and it makes sure that it's these homomorphisms do not cross each other, right? So the depth of the rule cannot be bigger than the depth of the typing chain of the graph which you are applying, right? I say sometimes depth, sometimes height, sometimes length, but that's the n which was in the definition you saw earlier. So you have these blue arrows which are representing the matching. And of course, so what you do in the bottom is the usual stuff. We do the push out to get the D, and then here we do a final pullback complement to get the target out of the D, which you create in the first step. And what's the idea here is that what Uwe will show you soon is that we get this T with all its typing type compatibility for free at the end. Yeah, so the chain morphism is a type in chain morphism. It's simply a set of graph homomorphisms with, or do we say family? Yeah, a family of total graph homomorphisms with this function f, which takes care of the indexes. So basically, it takes indexes of the source of the G typing chain and maps it to indexes in the H typing chain, and making sure that it doesn't go crossing like each other. It goes always parallel with each other. So it could be, it's also a necessity that n is smaller or equal to m. Yes. Now to summarize before Uwe takes over, we have some parallels. We say the type graphs, we have these multi-level typed graphs like L, I, R, S, D, T with these multi-level typings. You see here. The type graphs are typing chains. So you see in here, this the things with the Gn to G0. The H is a multi-level typed graph. And you have the type morphisms, which are like this mu, lambda, and rho. Yeah, a second. And these are living in different categories. And here's the idea, what's a brilliant idea of Uwe, we're coming up with this inclusion chains in order to make this uniformly and nicely in them, like as Reiko was saying, always methodologically. Yeah. So now I think Uwe should start.
Sorry,
but
Aaron raised his hand.
Aaron, you have a hand?
Yes, if I may, there one more or less technical question about this typing chain, and it's something that has occurred to me before. But in going from the the first level to the 0th level, you do some something else. Then seem to be doing something else than going between all the other levels, because on the first level you have an edge that corresponds to something that is essentially a node on the 0th level, right? With incoming and outgoing edges on the 0th level. You see what I mean?
I mean, you mean between MM0 and MM1 in this picture?
Yes,
yeah.
yes.
Yeah, this is the only thing is that here there's this between MM1 and MM0 there's only there's no other level, so this is a direct and a total morphism.
Yes, but that was not my point. The point is that the nature of this mapping is different from the nature of all the other mappings. In all the other mappings, you always map a node to a node and an edge to an edge, which is the natural way of typing a graph using a type graph.
Yeah.
But then between MM1 and MM0, you're doing something else. You're taking an edge of MM1 and mapping it to a node of MM0. No. Yeah, I mean, your example right at the beginning also showed this. Yeah, I mean, yes, here.
No, here
the edge creates is mapped to. Well, here you represent actually E reference as an edge, but I think it's typically represented as a node on the MM0 level. Maybe you actually solve this by doing something else than the standard thing. Okay.
Yeah. So we have this jump between concrete and abstract syntax, and we somehow packed it in this here. So we are aware that there's something happening in between here.
I retract my question. Right. I thought you were doing things in the same way, and now I should have looked more carefully and see that.
No worries. But this is okay. So let's go further to Uwe.
Sorry, just to understand the background. So what you were referring to is the way it's done in kind of MOF or mainstream meta modeling, isn't it?
Yes.
Where you
Yes.
have a meta class
For e-reference, yeah, and you have a meta class for
then appears
attribute
as
and all these things.
yeah. Okay.
That's completely true. That's completely true. The only thing is that there's this change between concrete and abstract syntaxes and these things, and for simplicity, you're saying, okay, we just represent this as an arrow, and then in the one that time comes, we need to have properties for the e-references and all these stuff. Then we take care of this. Actually, it's just
Thank you.
Okay, thank you for the question. Now, Uwe, you want to?
Okay, let's see how we can do this here. Yes, as Raiko said, so now comes a more methodological thing. I mean, we had a lot of very nice and intense discussions. Sometimes finds it was really fun, and many rounds. So coming back to what Adrian already explains. So what we have here, what we end up is with this picture here. So we have two, I don't know if this is better, two different kinds of nodes. Yeah, we have graphs. Here on the bottom, we have these typing chains here, and then we have three kinds of arrows. We have graph homomorphisms on the bottom. We have these multiple typings of graphs over a typing chain. And we have a morphism between typing chains that maps this change of the rule to the probably much longer chain in the modeling hierarchy. So, and now comes the methodological. Now it's here. Yeah. So we cannot state in a natural way that the diagrams are assumed to be commutative. So, and now comes the methodological question from my side. Can we transform the left diagram, this diagram, into an equivalent diagram with exactly one type of nodes and one type of arrows? Now that we have really a uniform approach. And the observation we can make here is that we actually do have a candidate here. We do have a category chain of typing chains. And now I'm doing these definitions again. So that's a typing chain. Yeah, so we have a sequence of graphs. We have, for any two graphs, I mean, with different indices in this sequence of graphs, we have a partial graph homomorphism. So we map a subgraph of GJ and a homomorphism from a subgraph of GJ into the graph GI with these conditions. So total the things to the graph homomorphisms to G0 should be total. It should be transitive here. So we have these transitivity condition. If I have a typing in two steps, then it should be also possible to have these in one step. So these transitive types. But here we can have more types. Yeah, so, and connex, that's a really thing. It took me a lot of while. The point is the following. If you have one node or arrow here, and you have two transitive types, it can only happen either they are equal, or they are in this way, or they are in this way. So there is no divergence of typing. And in these diagrams, it becomes, yeah, you can formulate it in terms of these partial graph homomorphisms. You can formulate it in this way as it's formulated here. It's kind of technical, but it took me a while to come up with this, but that's at least the intuition side. So then we have typing chain morphisms. Again, we have now two typing chains. So the second one is longer than the first one. So we have first to tell where the indexes here are mapped in such a way that we are not making the jump smaller. So the jump should be at least the same level or even higher jumps. And then we have a family of total graph homomorphisms, again, that we have this inequality here. So the typing can be more fine and more expressive on the right-hand side as on the left-hand side, but at least the typing I have here, we find it back here also. And this is closed. If this down here, this thing is a pullback, this means that we have an equality here instead it is just an inequality between partial graph homomorphisms. Good. Obviously, this can be composed, so we get a category of chain. So, and now these are I will spell out here what we can do. So what we have to address here, if we want to do this, to transform, to work with only one type of nodes and one type of arrows. So we have these multiple, these chain here, this multi-level typing of a graph L. And what we want to have encoded as an arrow in the category chain. Now we have to extend this graph into a typing chain and then have here a typing chain morphism between these two typing chains. The second one is here we have these multi-level typed rules. So these things we can here, and we want to express this as a commutative diagram in the category of chain. So yeah. The second one is here we had, again, what happens here, Adrian?
Something is wrong with the style. Sorry.
So it was correct there, but okay, good. Here again, here we have now three types of, originally three types of arrows. We have graph homomorphism, multi-level typings of graph, and we have these typing chain morphisms. And we would like to have corresponding so we have some technical conditions. What does it mean that they are compatible? And we want to try to express this as a commutative square in the category of chain. And then describe the first step here. So in the original, we had to push out of graphs down here. Now we want to have the same thing as a push out, expressing as a push out in the category of chains, such that this typing of this resulting chain is just given as a mediating morphism for this push out here. And in the second step, we want to have, so we have now generated these two guys here, and now we want to have, we have an underlying finite pullback complement construction C, and we want to have, just construct here this typing chain and close these things. So I will come to back this later. Good. This is the original idea of what it means that we have multi-level typing. So we have this typing chain here. Then we have a graph and H, and then we have all these partial graph homomorphisms for each level, for each index, satisfying some inequations. And the question is, a trivial, that's a very trivial observation. Now we have here these partial graph homomorphisms. So we have the domain of definitions of all these partial graph homomorphisms, and we can just put them each under the other. So we have here a sequence of subgraphs of H. So that is H0. So it's H. And a simple but interesting fact is that any sequence of subgraphs of a given graph can be equivalently presented as a typing chain. So this was a big, not a big, but was a kind of nice surprise when I had. What we do is, so we have now this sequence here of subgraphs, and to define these partial graph homomorphisms, we just take the intersection of these two subgraphs. For each for all the indices J and I, we just take the intersection of these two graphs. And it can be shown that this gives indeed an inclusion chain, so satisfies these properties of an inclusion chain. And then, okay. Yeah, that's now, the point is that we can now express the original multiple typing as a typing chain morphisms. I may not go through this. This is a corollary we have to prove here. So the situation is as follows. We start with this graph H that is typed over this typing chain. We collect all these domain of definitions here. We consider construct by intersecting all these things a corresponding typing chain morphisms, a corresponding typing chain. And now so a partial graph homomorphism is given by a subgraph. Here we subgraph plus a total graph homomorphism. Now these corresponding total graph homomorphism give us a typing chain morphisms between these inclusion chain and this typing chain. So this is something to prove there, but that's this can be done. So good. What we have done now is to transform these multi-level type graph into an inclusion chain plus typing chain morphism. So we have these three arrows. And now the question, what about this graph homomorphism? So, and it turns out that we can lift this graph homomorphism into typing chain morphisms between these two inclusion chains here, L and I, and these two inclusion chains R and I respectively. And what we get are so-called reduct morphisms. What is a reduct morphism? Yeah. And the original type compatibility of the rule that we had formulated somewhere correctly becomes now just the requirement that we have commutative triangles in the category of chain. So what is reduct morphism? This I found out only in the third or fourth round of trying to understand and reorganizing everything. The idea is very simple. So here we have multiple typing of I over this, and somehow the typing of L should follow from this typing or should be obtained from this typing. And what I actually do here, so here I have the sequence of all the corresponding partial graph homomorphisms from L into the different levels of this typing chain MM. And I just take a level-wise pullback. Yeah. So here I have the basic graph homomorphism, and for each level I just define the corresponding subgraph of G by a pullback. Yeah, so level-wise a pullback, I get a sequence of subgraphs of G and this inclusion chain, and then we can get this. And these are reduct morphisms. So reduct morphisms can be constructed or are given by basically by this total graph homomorphism on the basic level. So good. Now we have this, so yeah. And now we had this compatibility condition for a match. A match was a graph homomorphism, mu down here, and the typing chain morphism here, satisfying some inequalities, typing inequalities. And this can be now, and this original condition, type compatibility condition for matches can be equivalently reformulated by two conditions. So we have seen before that L is a reduct, okay, here, that L is a reduct of this typing here, yeah. And now these original conditions we had for a match can be now reformulated that L is a reduct of S along this graphomorphism. So we can reconstruct L from this typing chain, from this inclusion chain, by taking the reduct along mu. And the second one is the resulting square of type chain morphisms commutes. So now we have reformulated everything or transformed everything in the category of chains. And now we can reformulate our objectives concerning the pushout step of rule application in the following way. So we have now this span of reduct morphisms, and we should construct the pushout of the following span. I will try to talk about this later a bit more. So the constructed pushout object D should be an inclusion chain, while the constructed typing chain morphisms should be reduct morphisms as well. So in other words, so this was not so clear in Adrian's part, the pushout in chain should be fully determined by the construction of the pushout of the span of these total graphomorphisms we started with. Mm-hmm. So that's the whole point. I mean, this that everything is actually induced or triggered by what we do on the level of the regional graphs. So the typing is just computing the corresponding typing should just follow from this pushout construction. So now we analyze a little bit. So we have to take the pushout of this span of typing chain morphisms. And then we have to look at the indices. So these have the same length. So this reduct morphism is bijective with respect to levels. But M is usually bigger here. Here we may have more levels. So the resulting typing chain should have therefore the level, the length of S. Yeah. So, but the rule provides only information about how to extend the subgraphs here of S at the levels that are reached by this F, that F embeds these or translates the indices here to the indices here. And for the this was 1, 2, no, it comes to. For the subgraph in S at levels that are not reached by F, so the rule doesn't impose anything. So the idea, was Adrian's intuition, we let just the subgraphs unchanged. So, and in terms of typing chain morphisms, so this means that we should factorize the reduct morphism μf into 2 reduct morphisms, and that we construct the resulting inclusion chain in 2 steps. Yeah, so we are splitting the original typing chain morphism. We just take all the levels out of S that are affected by the rule. This is this S down arrow F. Mm-hmm. And then we have here now a sequence of a subsequence of these sequences of subgraphs of S. This is here this. We just take this. And these 2 reduct morphisms share the same family. So mu is actually the same family of graphomorphisms. And then this guy here is doing nothing. Yeah, it's just introducing some, we have a sequence of graph, it's just filling some graphs into this sequence that haven't been there before. So, and then we do this. And that's really straightforward. So for the given span of inclusion chain of length n plus, we construct an inclusion chain here also of the length n plus 1. And for each level, we constructs the corresponding subgraph of D by a pushout in graph. And now comes the point with this reduct. Since these two are reduct morphisms, so generated level-wise by pullbacks, the Van Kampen property ensures that we get reduct, that this also becomes reduct morphisms. So the resulting square becomes, and that's of course, that's something to prove here, and I try to do it. The resulting square becomes indeed a pushout in chain. That's the easy part. The second step, as I said, so we have done everything that here, we have done everything that is imposed by this rule. We have added all these things that are imposed by the rules. And now we just have to fill in the holes that are left here with the corresponding untouched graphs from the original inclusion chain S. Yeah, so if I have an index here in on this side that is reached by F, then I take just what I constructed here, and if I have an index here on the right-hand side that is not reached by F, then I just take the original subgraph SJ from this inclusion chain. Okay, I have to say it again. I'm not really an expert in graph transformation and even not a so big fan, and I had to push myself again and again to prove in detail that Adrian's intuition was right. I mean, this intuition just to fill the things by the thing, just let take the things we have there before. And that was so tiring, and I'm only 95% sure that it's correct, but at least I tried to do what I could do here. So now we have a pushout. So the composition of two reduct morphism is a reduct morphism as well. Composition of two pushout squares results in a pushout, so we get in such a way the desired overall pushout. And as discussed before, so because this is a pushout here and this left front here commutes and this triangle back commutes, so we get corresponding unique mediating morphism here that gives us multi-level typing of the constructed graph D. Second step, so the idea is we take this finite pullback complement of graphs, and then we construct the corresponding, I mean, this should be a reduct morphism, so we just construct this reduct morphism. Yeah, for each level I, we take this pullback here. So then we generate all these subgraphs of T here, and by this construction, we get a reduct morphism here. Then the typing is just borrowed here. We take this typing chain morphism composed with this typing chain morphism, and we get this typing chain morphism. So it's just by composition. And the tricky part is then to get these, to establish these typing chain morphism. And this was, again, so tiring. I mean, so the missing typing chain making the diagram commute is simply given by composition and decomposition of pullbacks and graphs. So it's just to check that you have these squares, some pullbacks there, and then this also becomes a pullback. And so, and intention, so this I have to confess. So we start here with a finite pullback complement and graph, and we construct in a uniform way. We construct in a uniform way, no, let's see. Yeah, we construct in a uniform way this diagram of inclusion chains and typing chains and typing chain morphisms. But don't ask me if this is a finite pullback complement in chain or not. So I looked a little bit on this, but I just let it as an open problem. So it's maybe also not so important, at least for practical thing, it's maybe not so important. So the important thing, I mean, Adrian can maybe say something. The important thing is that everything we do now on this multi-level type or in this category of chain is induced what we do on the real graphs. Yeah, so everything we do, the typing, all the multiple typings we have to compute, all this is done or is triggered or induced by the things we do on the basic graph structures. So you want to have the conclusion or?
Yeah, no, I think you can take it.
Okay, so what we have done is we have shown that type graph transformations can be generalized to multi-level type graph transformations, improving preciseness, flexibility, and reusability of transformation rules. So this is Adrian's part. So, and that's now here. By introducing the category chain, we have been able to establish the necessary concepts, constructions, and results, I would say, in an adequate and well-organized way. And so, and this was a requirement that was implicit when we discussed. And our approach can easily deal with parallel, independent, multi-level typings of graphs and rules over supplementary hierarchies. Can you say some words about this?
Yeah. So this is one of the ideas which was pushing about multiple typing. So you saw in the picture, so you have these tree-shaped hierarchies, like you have one common type, and then everything was typed over this in different branches. But it's also possible that one of these graphs somewhere has a typing and a parallel, a supplementary hierarchy, which means that okay, I want to add, say that this is not only an employee, but he's also a patient, or this is not only a patient, it's also a customer somewhere, and these kind of things. So you could somehow tag these different concepts with different types, and these types coming from different hierarchies with its own rules and everything. And now the idea was to how to make rules which are working with these multi-typed concepts. And this was basically using this same technology here, and these ideas here it was working also for amalgamation of these rules. So you're saying you have instances where you have types coming from different hierarchies, and now I have a rule which is defined in this hierarchy, another rule defined in this hierarchy. I can put these rules together based on some commonality with these so-called kernel rules, and then amalgamate these, taking, of course, care of priorities and taking care of conflicts and these things. Of course, you don't want to add something to a deleted thing and so on and so on. So this is taken care of. But at the end, this way of thinking was helping us to also push it further to the next step, like saying, okay, we can do amalgamation, we can do interoperability and all these things which are coming beyond these ideas here. Yeah.
So, and just a last remark, technical details can be found in this LNCS paper from ECGT 2020, but the real technical things are in this TR. And I don't know how it's general in the world outside there, but, you know, I mean, all these, this server where we had our technical reports is gone. I mean, they are centralizing everything, and now, you know, you cannot approach anymore these technical reports over the page of our department. It just disappeared. But I think I put it at least.
I think we have it in archive.
In archive or in ResearchGate at least.
Yeah.
So good.
And also Fernando's thesis is also covering some of these things, especially the nice figures.
Yeah.
I mean, the things which we was showing you, the domain of definitions and how to make the inclusion chain, these things are like done for examples. And it's yeah. Before you look at the examples, you have to understand that the definitions, but you don't understand the definitions if you don't see the examples, at least if you are applied.
And Fernando never, and he was really postponing it to look at the definitions, but at the end he said, oh,
Yeah.
It was really helpful. So good.
Yeah, thank you very much.
So that's it.
Okay. Okay, very good. Thank you very much. So I wasn't even aware of how close I was with the actual specific topic of this talk when I described.
Yeah, you were the opponent of
experience,
Fernando,
but,
of course. You read the thesis, so yeah.
Well, yeah, but okay. The roles were not so clear just from reading the thesis. I could have guessed maybe.
Yes.
Right. Very good. I have a couple of questions, if I may. So the first is maybe you said it, Uwe, but maybe it was too much too much detail there. So these two categories. So the category of the graphs typed over the chains. Okay.
This was never defined as a category.
Oh, I see. So okay, so maybe then that's why that wasn't stated explicitly. I was wondering whether the category of graphs typed over the chains and the category of type change, including the graphs with these inclusion things, whether they are equivalent.
No, because what you do actually, I mean, if you do the category of graphs typed over a fixed typing chain, then you have something comparable to a slice category as a category of typed graphs.
Yeah.
But what we actually do, and then you have to look if you have a kind of, I mean, you have to, then you get the kind of index category. I mean, if you choose a typing chain, for each typing chain, you get this category of graphs typed over this fixed typing chain, and then you may get an index functor if you know how to translate. And then you take the Grothendieck.
Well, that's probably one I was thinking of, yes.
Yeah, but this is only a subcategory of the category of typing chains. But this is actually I mean, I'm even working with Redux, so we have very, very special pushouts that we are constructing here. But the category of typing chains itself is even bigger what you get by this construction.
But there seems to be a kind of canonical construction of the typing chains from the typed graphs, in the sense that you basically take the domains, the partial typing morphisms, use them as the graphs that are in the inclusion chain, isn't it?
Yeah.
I don't know whether that's a left adjoint or right adjoint or not a joint at all, but it maybe.
But you know, I mean, this was Adrian's idea with these level typed, and then then I tried to formalize, but I never went further to say now we take this category and it was enough to, There's a lot. I mean, if you really want to play around, you can do all these things, and you are right. So
okay, but I'm happy if you say that is sort of capturing the intuition. Whether it's fully sort of worked out, obviously, is a question of the complexity of it to some extent.
So the point is, if you do type graphs, then you get a functor from the category of graphs. I mean, the slice category construction gives you a functor from the category of graphs into the category of categories. Yeah. But here, I mean, these kind of that you can this interplay of typing chain morphisms. So, and this category of graphs multi-level typed over a given typing chain, how this I mean, this is something that we have been not interested in how to see this interplay. We just, it's not so, it's not, it should be possible, but it was not in our focus.
Right. So the other question maybe is more conceptual. So is it possible to flatten this type hierarchy by taking some kind of you're grinning, I'm sure you had the discussion before. Kind of taking some kind of co-limit also over the type chain merge everything into one graph and remember somehow which type was defined first at which level or something like that. So have a kind of annotated type graph, sort of a single annotated type graph representing this hierarchy rather than a series of graphs, and then map the type graph into that.
Yeah, of course you can flatten. I mean, we did this in some of the works. I think it was in the time when Alessandro was in the game.
Probably. Maybe I
Yeah.
remember it from there even.
Yeah, so you could do the flattening, but the idea was that we wanted to keep the same structure as we have in the multi-level modeling hierarchies,
Oh.
and work with that instead of flattening everything to one level.
Yeah,
And at the end, what procedurally what we have is that in the implementation is that we are generating. If you remember, I mentioned the proliferation of rules. So what we do is that with these multi-level rules, we match it with the target hierarchy. I mean the hierarchy of the source and target graphs. And what we do is that we are generating a proliferated rule, which means that exact rules which are needed to be run. And these flattening to 2 levels was necessary to do at the end for the implementation reasons, because yeah, it's naturally more available engines to do it in a 2-level way. But at the end, so what we did, it's already 3 years ago, 4 years ago, we went to MOD with some collaboration with the University of Malaga, and we implemented an engine which takes these levels as they are, these hierarchies, and manipulates it as it is without flattening it to a 2-level hierarchy.
Yeah.
And that's a work which one of my PhD students was working mostly on, Alejandro. And yeah, of course, we needed to do a lot of creative things like this operations for gathering multiple hits, multiple what's called matches and these things. We call for magical boxes even, because it was like working like a magic. But yeah, it was interesting that we could even do it without flattening.
But I'm not sure if it's really, I mean, in what way this is equivalent. I just remember I had a paper with Harald at Models 2021, where we did a general methodology for internalizing multi-level model typing.
Okay.
There is, I mean, we found it. I mean, I was telling him, and then he was not believing that he found the lemma from, Avodi, I think. But this works only for total graph homomorphisms, not for partial.
Okay.
Yeah, so if you have total graph homomorphisms as these typings, then you can internalize it. I mean, flatten it, and this is equivalent, but with this partiality, there comes this. But yeah, so if you want, Raiko, I can send you the paper.
Yeah.
I mean, you can do it, but only for total, and then it's equivalent.
Makes sense, I think. So I mean, so that is related to the other thing I wanted to check, but maybe I can quickly ask that question, and then Andrea can.
Yeah.
So, you mentioned that you had this. I don't know whether you've done it already or we're just discussing it about typing in different type graphs that are not part of the same hierarchy, kind of orthogonal typing or whatever you call that.
In 2 hierarchies, yeah, you can have it, or in 2 typing chains, yeah.
Or in 2 typing chains. I was wondering if the general case is something like, I mean, from a practical point of view, this sounds very familiar in the sense that you have applications that have data that is defined over different domains, and each domain has its own ontology, let's say. So if you want to, I mean, of course, you can make an application-specific data model that captures everything, but if you have kind of, if you want to use standard ontologies, then your data would be typed over different ontologies in some overlapping way, and these ontologies themselves are somehow related. So essentially, I would say you have a diagram of ontologies or a diagram of type graphs, not typed graphs, but a diagram of type graphs with relations between them. And I mean, you can think of total relations or partial relations, but if you have total relations, I mean, maybe you just have the intersections represented explicitly. So you can think of a diagram of type graphs with total morphisms between them. And then somehow, I mean, either you take co-limits over these things in order to define the typing from the graphs that you want to type. Or again, you work with partial morphisms for the typing. But what I just understood from your comment was that your approach was more based on saying I have multiple typing hierarchies and type into multiple typing. So not a kind of completely flat or kind of network-like approach, is it?
I think yes. So the point is, I mean, I had the pushout construction here, but this works only for reduct morphism, and anything else, any other kind of co-limit becomes so complex, and I would say it doesn't exist. Because you cannot really merge. And when I remember right, what Alejandro did in his PhD thesis was to keep these different two hierarchies separate. But the whole machinery I developed here is just to say, okay, what everything is actually induced by the pushout in the category of graphs, the typing. And this allows that you can work with so many typings in so many different hierarchies as you want. Yeah, you just compute these different typings, but the underlying pushout for the graphs is the same. This is more or less. It took a while, but this is the essence of the theoretical part here.
Yeah. Okay. Thanks.
May I ask a question, a basic question about the approach of defining rules and rewriting? So probably this is something very standard in your approaches, but the representation of rules as cospans, the construction by playing with pushouts and then final pullback complement really triggers the question whether you can do the same by having spans and having first like in the sesqui pushout, first some kind of final pullback construction and then the pushout. Is there a strong reason why to have this cospan representation?
This is a standard question we are getting. So yesterday, I actually tried to look back at the papers to see. You actually mentioned sesqui pushout in the papers, but yeah, you answered.
So I mean, this is something. Okay, the point is the following, because I mean, this is now graph transformation. But if you, I mean, we had these things. If you really work with models and let's say you introduce new things with some attributes, with some properties and then you delete some of the old things, but the properties of the new things you introduce depend on the properties of components or items you delete later. So my whole point is, if you really want to describe transformation of systems, you need a space where you have both things, the old things and the new things together, that you can transfer the properties from the old things to the new stuff, and then only then you can delete the old stuff.
Okay.
And therefore, I was always insisting that we should look at cospans.
Okay.
So this is more a methodological thing, and we don't know if things are equivalent or not. So we have been just happy that we went through with these things. But from my point of view, coming back to Reiko's nice characterization, from the methodological point of view, I would insist in many situations on a cospan, exactly of this reason, that you create new things and the properties of the new things depend on the properties of the old things that you delete later. If you first delete, you cannot transfer the properties. So this is a very abstract methodological thing, I mean, vision I have, and therefore I was always insisting that we look at cospans.
I see. No, this is very, very convincing answer, probably in the realm of standard graph transformation. You don't have this problem because you are really local in the application of the rule, context-free. Therefore, removing something you don't have effects which don't allow you to add things. But I understand perfectly the situation. And another question of the same level of stupidity. The idea of having different hierarchies and type hierarchies and having entities which could be typed over both clearly brings to my mind the problems that you have in object-oriented programming with multiple inheritance against single inheritance. Do you have in any way some similar situation, or the way of modeling and of describing behavior is far away from object-oriented programming, therefore you don't run into these problems?
Yeah, I mean the idea with I mean in object-oriented modeling we still allow multiple inheritance, right? It's when we come to the implementation we avoid it for good reasons, right? But in our cases, I think in the applications we've been considering, it was not introducing problems actually. It was more like just for tagging mechanisms to say what kind of types these elements have, right? So you might have different types, and then you apply the rules which are coming from that type. In the cases before we did amalgamation, we're using these multi-typing or like the supplementary hierarchies to, for example, introduce new techniques. In one of the papers of Fernando, we were using it for runtime verification, for example. So concepts and rules for runtime verification, defining formulas over how a system should behave, checking the rules at this, if this happens, then this happens in the end, and so on and so on. These temporal formulas. For this, we're having a hierarchy for itself. So you have an hierarchy talking about runtime verification, defining the formulas and checking these formulas. You had another hierarchy defining types for saying, okay, what kind of movements a robot can do, for example, or what kind of movements a drone can do, and so on. And then putting these two things together, one of them was taking care of the evolution of the system, like the robot goes right, left, up, down, blah, blah, blah. And then the other one taking care of if the robot goes left, then it should always go to right again later, and these kind of things, right? So you have two different systems, two different hierarchies taking care of two different ways of like the behavior of the system. So this was the way we're using it without like I mean, both sets of rules were running on the same system separately, and it was somehow making sense at that time, at least. And then later we came up with amalgamating the rules. Now it's not only that these one of them is taking, for example, care of the runtime verification of the system, the other one of the simulating the system. Now it was like two systems simulated at the same time, right? So as I was mentioning earlier, I think one of the examples you're using was like these software engineering company, and you have an insurance company. Both of them are processes, right? And then suddenly now you have a software engineering company which also has insurance cases, right? Then you have to put these two systems together, and the rules from both sides of the world has to be applied at the same time. And this is quite interesting to look at the end. Yeah, I'm not sure if I answered the question, but it is an approximation of it. Yeah. And it is, I mean, this idea with like multi-dimensional multi-typing is not new, but we tried to incorporate it into it because it was a natural something which was pushed us to do it. And we were at that time we were looking also at Petri nets, and we were looking at different kinds of Petri nets, like colored Petri nets and time Petri nets and Petri nets with special domain-specific concepts and these things. And it was quite nice to see that you could have these different rules with different kinds of Petri nets, and you could have a Petri net which could have, for example, both the concept of time, the concept of colors, these multisets and these things, and you could define an instance of this which was respecting the rules of the ingredients, like of the types. Yeah. And of course, when you do amalgamation, then you have to take care of these conflicts. Conflicts of these rules. I see. Okay, with the multiple inheritance, you get these problems with sometimes conflicting. But now what we do is that we do not put two rules together if we find out that they are conflicting in some sense, and we have defined the rules for conflict, which is blah 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 blah. And if you check these, so it will at the end it should be going up and not. Yeah. Yes, Uwe is pointing the watch. So.
Okay. Any other questions? Otherwise, oh yeah, Niklas has a question.
Yeah, first of all, thank you both for the nice talks. And this may be more a question for Uwe. So in the beginning, when it started with this defining of hierarchies of types and properties, I would almost have guessed that you might say at some point that this is somehow related to generalized sketches. Is that something, I mean, am I completely on the wrong track, or is that something?
No, they come just on top. I mean, that's no, this has, I mean, it's I mean, Adrian said we are not talking about models, we are only talking about the underlying graphs.
Mm-hmm.
But the point is, if you want to talk about models, I mean, you just extend the graphs by these constraints, and then you get models. Yeah,
because that was sort of the question. So in principle, on top of these typings, you probably also have rules or constraints that you might also get as an input from users, like certain sort of an external system of constraints for these typings that it must be respected. Like
no, this is not what we are doing. I mean, we are doing a model as a sketch, and the sketch has an underlying graph. So that's usual. So, and we are transforming. I mean, this was Adrian's thesis that we can control by these constraints we have on a sketch. We can have a better fine control of applying transformation rules and so on. And the other dimension is, of course, I mean, if you want to do now e-graphs instead of graphs, this should also work. Yeah, so I mean that's I mean this is kind of at least as long as I can. This is kind of generic what we did here with these typing chains. It's not so much depending on graph. It is just that I mean it's if you take instead of graph and any other pre-sheaf topos, you should get the same results.
Okay. And have you, so you mentioned briefly Petri nets and then some model-driven engineering and some other applications. So you said this is implemented somewhere for concrete applications, or was there some motivation from practice?
We have a tool called Multicore, and it had a website before, but this website is closed down. Now you have to go to the GitHub or the Bitbucket repository. From there, I can send you the links and the things. So in there's a folder called examples. In that examples, you see tons of implementation of things which some of them might be working, some of them might not be working because of it's based on Eclipse, and Eclipse, it changes structure, then things get out of date. But I think
because I wanted to offer if this was something, I mean, maybe we could put a link on the talk description if people wanted to go further.
Definitely.
Because some people might watch this after the fact and then, yeah. Thanks.
After summer.
Thanks a lot. Thank you both. Yes.
Yes. Thank you. Yeah, bye-bye.
Wait,
so then let's close maybe the formal part of the seminar. And yeah, thank you very much again for the talk and everyone for attending. And we say goodbye until the end of the summer, essentially.
Oh, I mean, are you not coming to Holland?
Oh, yeah.
Yeah. So I will see you there.
Yeah.
Okay.
Me too.
Yeah, we are still online or not?
No.
For the purpose of this seminar, I meant we say goodbye.
Yeah, but it was streamed live, right?
Yeah, we will actually now close the stream. So maybe for everyone who was on the online audience, just to say, as Raiko said, we return in the end of the summer, and we have an open call for contributions. So on the GReTA page, you can find a button where you get linked to a speaker registration form where you can register yourself or others if you wish. I mean, others only with consent, evidently. And yeah. Thanks everyone for attending, and I'll now close the live stream. I think some of us might stay for a quick second, but